All right, welcome in, guys. We're going to continue with some rotational dynamics and equilibrium. Last time, I told you a little bit about torque and also a little bit on center of mass. Before I get into what the slide says, I want to sort of refresh a bit on center of mass. I found where they kept everything. And I have a lot of, you find these in like novelty stores. These are little toy birds that have the center of mass almost not on their body at all. So they have their wings spread, and you can balance them right on top of their nose. And what's going on is that there's like weights in their wings. And all of the mass from one side is countering the mass from the other side, and the center of mass is right where the beak is, right on the front of the nose. So imagine something like this. From last time, we were just finding the center mass of something in a straight line, and there's conveniently this rod that's also in between them. I can balance it right on the center mass. Let's do it like right there. The rod is bent a little bit, but we have that type of system. You get little fun things like this. Balance them. And this is the basic premise of like people on a tightrope. So kind of like this person here, this little toy, going on is someone walking a tightrope holds this really long bar. It's like a conventional tightrope, not like one of those slack lines that like bounce. So imagine a tightrope, someone's holding this, they can say they start feeling themselves falling, they can just move a lot of the mass that way to pull them back up. Or place the center of mass back over the top of the wire. So as long as the center of mass is being supported, like that. This is being tricky. Okay. As long as the center of mass is being supported, whatever is in the system will remain in an equilibrium. So that's kind of like this thing right here. It stands on its own, but as soon as I flip it over, now, where's the center of mass is roughly in the middle, but if you trace a line straight downward, it's not being supported directly underneath it, so it'll fall over. I don't know if this wine's that one bottle. Back down here. So we have this, and it will fall over. That's the principle of like you're in a chair, you tilt backwards. There's that brief moment you feel it's like trying to pull you backwards. That's because your center of mass is, like this object, no longer being supported by any of the legs underneath you. That's why on stools or anything, the legs sort of project outwards to make a bigger area for you to sort of sit in. Like that. What else? I had this, brought this in. Just a fork and spoon I put together real quick with a toothpick to put in the middle. And even though it looks like this thing is going to go that way, if I balance it on this water bottle, if I do it right, I'll do it after class. So, and you saw a picture of it last time. So, as long as the center of mass is being supported, the object will be stable. You see this everywhere in nature, organically. It's the basic principle of trees. And why do trees have branches that go out everywhere? It's because they're trying to balance themselves. If they only have one branch that goes out one direction, then they'll tilt that way. But if they have one going that way, one going that way, maybe 40 more in various directions, they have a lot of mass surrounding them. They have the center of mass being supported, which is basically in the center where the trunk is. This bird, this that. And the final thing on center of mass, you get something like this. I only have about, like 7 planks here. And this top plank right here is not being supported at all. It's not over the table. Right here. I don't know if I can put it back. There we go. It's not over the table at all. This is, one big system, and the center of mass is right here of the whole construction. This is like a principle of how bridges are made. Bridges have to arc a certain amount in order to support itself. So one side arcs that way, the other side arcs a little bit. The center of mass is stable and being supported by this. And then you have like a road over it, another side. All right. So that's some review on, or just some examples of center mass. About torque, I got one thing wrong. I want you to scratch out, or at least replace, is I said torque. I said F cross R. I want you to flip them. It's R cross F. So R cross F. So wherever you have written that down, I want you to replace it with this. This basically means R times the tangential component of force, or you can just think of the force, I guess. I'll review that later. Force times sine theta times sine theta. All right. Then we can go into a little bit more on rotation. Torque is a force. And if we're looking at forces and how they make things rotate, well, maybe there's something that's similar to forces in, the linear sense. We already covered forces. We already have a set of rules. Does anything match? That's my main question now. So, turns out there is. So, when a solid object like this disk, or a wheel, or maybe this, you can imagine this is like a planet and a moon, it's like rotating. Whenever a torque is applied, and a proportional angular acceleration appears, or is created, I should say. And this matches closely with Newton's second law. Remember, Newton's second law was force is mass times acceleration. Where I have, a force that is, how do I want to write this? It is proportional to acceleration, linear acceleration. So if I give something an amount of force, it will accelerate in a predictable way. What I'm saying is that if I give something a torque, if I force this disk with a certain torque, then it will speed up and gain some rotational acceleration, or angular acceleration, sorry. So it's proportional. I don't want to do that because it's too many things that look like alpha. I will say, here's what I'll say. proportional to the angular acceleration alpha. Okay. Okay. That pretty much makes sense. If I force something to twist, it's going to speed up and twist more. That's what I'm saying. Okay. How do I prove this? So let's start with Newton's second law. So let's say force tangential is equal to mass times acceleration. Tangential. So this is just like the irregular case we've been using for so long. This is linear. Tangential, or you might say transverse. That's I'm saying something moving in a straight line. And let's multiply both sides by r. R times tangential, mr tangential. Okay. What else? Now let's replace the tangential acceleration, or that straight line acceleration, with rotational acceleration. So if I remember, or I recall that tangential acceleration is r alpha. Okay, so let's replace it with that. We have r. T is mr squared alpha. And last step is, we know that a radius, or yeah, I should say radius times a force on the left side of the equation over here, that is torque. So we have torque is equal to mr squared times an acceleration, an angular acceleration. And this sort of thing we created at the bottom here, this mr squared, that's actually something important that I'll talk about next. That is, let's call it, yeah, I'll do that right now. Let's say that the letter I is mr squared. So in conclusion, I have torque is equal to I alpha. And this equation right here is a force equals some sort of mass combo I call I. So it's force equals mass times an angular acceleration, and that matches almost identically to Newton's second law up there. All right, but what is I? I just created that. I said make it one letter. That is what I'm going to call the moment of inertia. It's just the letter I, capital I should be specific. Every object has a moment of inertia. Go to, yeah. So moment of inertia, I, the capital I, let's talk about that. what did I say it was? mr squared. So however much mass you have, and however far away it is from the points of rotation, the axis of rotation. All right. So you can think of this as inertia for spinning objects. I'll add quotes. This is me saying it. Inertia for spinning or for rotating objects. And what was inertia again? It was how easy it is for something to do that. So that's just saying how easy it is for an object to start to rotate. All right, now we're getting somewhere. So we have a mass and we have a radius. And I said all objects have a moment of inertia. Down below here, I have two similar types of objects. And the black point on these is, you can think of the axis or the axle if it's a solid object. They're going to spin around that object, that axis. Sorry. So that's going to go that way. Okay. Well, if the moment of inertia is related to the mass of the object and how far away it is from, this pivot point, then I should be able to see it, clearly when I, try out some tests. Does anyone want to try a little demo? Yeah? No?
Professor?
Yeah.
What is the difference between moment of inertia and impulse?
Impulse?
Yeah, because
So,
it doesn't I also stand for impulse.
It was for impulse, right. They're running out of letters for everything. This is the more important one. If you see it somewhere out in the wild, it'll most likely be moment of inertia.
Okay.
Impulse was just like a small amount of force over time. It's typically only brought up when you talk about, I think it was momentum. That's what we were talking about. In this case, we're talking about rotation. Anything rotation, it's always going to refer to this.
Okay.
All right. Okay. Any takers? I always have to state, I'm not going to hurt you. I have two things I want you to try to twist. I have those, and I have two more. So we have like two people come up here. Alright, awesome. So, someone's going to take one of these, and someone's going to take the other. Alright, awesome. Now, what you guys are going to do is try to like twist it this way. Try to get the masses to spin. Right, yeah, with your wrist, like that. How hard is it to do that? Without it slipping. Try to get the whole thing stuck. Yeah. Yeah, I know, that's kind of loose.
I think I made it loose by doing that.
Try using it. Those are looser. Okay. Not too bad, right? Now go like this. How hard is it? Alright, so hold it like down like that. Try to back and forth. You go like that? Who can go faster? Competition.
Closer.
Right? That is closer. So let's switch real quick. That. Now same thing down here.
Oh my god.
All right, yeah. So that's what I'm talking about with these these use the same exact masses, same exact dumbbells are on the sides. It's just that that one over there has the mass out at a different radius. And so that radius is being squared. So it has a higher moment of inertia. Same thing with these. These are more direct. So try these. That's, you guys just pick one. And same type of competition in the middle, back and forth. Who can go faster?
Hit my palm.
All right. And switch. This is the same exact thing. It's more direct because you see there's only metal where, is it easier? I don't
know, I'm just trying to do
There's a lot of strain on your wrist, right?
Mm-hmm.
Trying to get it to change direction. That's the rotational or angular inertia or moment of inertia. All right. Anyone else want to try these two real quick? I'll let you guys.
Those ones are easier than those.
These are, yeah, definitely. Yeah, come on.
I just had a question.
Yeah.
What is the difference between both? Are they the same mass?
These are the same mass. They weigh the same. That amount of aluminum right here is the same as these two. They weigh exactly the same. The only difference is that on this one, the aluminum is in the middle, closer to where the pivot point is. Pivot point is my hand. I'm rotating it. Right? So right in the middle of my wrist to where the mass is, that's the radius. That's R up there. So that's a small value for this one. So something like that. This one, from here all the way up here. So that distance squared. So this has a much higher, that's hard to do, moment of inertia. All right. So let's actually try to calculate something for some vague shapes like this. These are two masses on a massless wire that's holding them together. So pretty much the same pictures I showed before. And let's say that we'll call this one mass 1. This one's mass 2. I'm going to compare these two. And the distance from where the mass is located to the pivot point, so right here to right here is R1. Okay, and this one, it's going to try to go around in a circle. It's going to make a nice little circle. Let's find the moment of inertia. Moment of inertia is, well, we're going to add up each object as it tries to rotate. So I'm going to say M1 R1 squared plus M2 R2 squared. Just to make this problem easy but not too easy, I'm going to make like a M1 is 10 kilograms, M2 is 10. R2 is 2 meters. Sure. So same distance away, same amount of mass on both sides. We have this. I'll do it real quick. 2 meters squared. Oops, sorry. So what do we have? We have 40 and 40. Moment of inertia for the left system is going to be 80. And how do I figure out the units? I just see what I'm multiplying. Mass and distance squared. So kilograms times meters squared. All right. That's the moment of inertia of that specific shape. If I change the shape in any way, moment of inertia is going to change. Let's do the left one. Same exact thing. All right, here we go. Now, from here to here is R1, but what's R2 now? We're always going from the pivot point to where the mass sits. So R2 is from right here all the way out to right here. So that is R2. It's much bigger now. And since I'm keeping these all the same, R2 is going to be 4 meters. All right, let's find this. All right, I'm just going to sum up everything that's rotating, find the total moment of inertia of this thing. All right, so we have 10 kilograms. This is 4 meters squared. So last term, it's already pretty significant. That is 160. This is 40. So the moment of inertia of the shape on the right is 200 kilograms times meters squared. So I have the same amount of mass. I just rearranged where all the mass was. Gives me something with a much higher moment of inertia. So this object is going to be, since it has a higher inertia, it resists more to rotating. That's what rotational inertia, moment of inertia means. So if it's a very small rotational inertia, it will start to rotate quicker. That's where I have this demo right here. Let me put this in front. So I have 2 wheels right here, and they have the same mass. Red and blue. You want to hold them? Make sure they weigh the same. Feel like they're the same?
They're the same.
That's it? Oh, they are the same. Okay. Feel acceptable? Oh, I'm cheating. Okay, no. They're both the same. They're both the same, but I look a little closer. The mass is arranged differently on both of these. On the red one, most of the mass is on the ring, on the perimeter. There's holes in the middle. For the blue one, right here, most of the mass is inward, towards the center. There's holes on the outside. They do have the same mass. So the question is, if I try to race the two, which one will win? What do you guys think? So who says red one? Raise your hand. Okay. And who says blue one? All right, let's go. Blue one. Why was it the blue one? Because the mass is inward towards the point of rotation. So that means it has a smaller moment of inertia. That means it can spin up faster, it can change faster. It has less inertia, resisting change. This one has this is like this system over here. It has a bigger moment of inertia, so it resists change more. So right at the start, it really didn't want to get spinning. This one starts spinning up faster. Earlier, I should say. Okay. You have those up there. Yeah.
I have two questions. So
Yeah.
first of all, because the radius is larger, it makes it faster. Is that the case in this?
The radius is on the blue one. The mass is more towards the center, so the radius is smaller, and so we have a smaller moment of inertia. And remember, inertia is resistance to change.
How do we know that the mass isn't focused towards the center?
Because you can see it right here. I'm going to get a little closer. You guys can see it. So we have right here, the red one is a large chunk of metal on the outside. See that? The blue one, most of the metal is towards the middle. You see it? Okay.
So does that mean that in this diagram here, the first diagram has one center of mass, and then the second one has 3 centers of mass? Or 2 centers of mass?
Centers of mass. There's always going to be one center mass of a system. For this, it's just saying that because this has it's extended longer, it's far away from the pivot point, it takes a lot more effort to get it to start spinning.
Okay.
All right. Okay. Let's see. All right, so let's say I have one point that is going to rotate around this black dot in the middle, and I can find the moment of inertia, just one point as it goes around some random mass. Well, then I can add maybe there's another point out here that is maybe right there. That's a certain radius and it's a mass. It's a single point. Now, well, what if this is also the same radius, the same mass? I could keep adding these all the way around to make a ring. Maybe I add another one. And they're all the same radius away. They're all the same r away. Maybe they all have the same mass as they go around. I could keep adding them and adding them and adding them. Then I could just keep adding all of these individual little points together to make a ring. Well, then what if I make another ring? It's a little bit shorter. And maybe another ring that's a little shorter. Eventually, I can find the moment of inertia of big solid objects. This is done mostly with like integrals and everything. I don't want to do integrals today. So I'm just showing you that you can take these small points, add them up as you go around, and as you add more and more and more of these just individual little points, and you add them all together, that's how you get into these very large solid objects. Except we're not adding, every single thing. That's taken care of by an integral. You just integrate over the area of your shape or whatever. All right. So this can be like a big solid disk. It could be like a CD. And actual shapes have been solved for, and you can look up on a table moments of inertia of shapes. You don't have to write any of this down. It depends where the mass is located, and it depends on how you try to rotate the thing. So compare, like the left side and the right side. They're the same shapes. They're the same shapes. They're just rotating differently. On this side, they are, I don't even have them. They are rotating with the axis going through the metal of the object, like this. Very easy to spin something like this. And so, we have a very, I guess it would be this one. Very simple and very small moment of inertia. Trying to get something to spin this way, with this axis. But then when I have an axis going through the middle of the object, I try to spin it like this. Now it has to compensate for a lot more. The length of the rod or whatever. And you can look up tables to find out, the shape of the thing you're rotating. Typically, if you're given a problem on this, they might give you the moment of inertia of like a specific shape. So something maybe really complicated, they might give you the formula for it already. However, we have shown that we can solve for very simple ones. Maybe just a single mass here and a single mass here, and they're rotating around another. We just did that earlier. So we know how to solve for these if it is simple enough. All right, so that's this one. There's also more shapes. So I wrote these up for a different class. They're all given to you already. If I'll say that if we have a test or something or a quiz on this, most likely I'll give you some sheet that has this on it. Doesn't mean that you can ignore this and completely forget what all of this means. You should know how to calculate for simple objects, like how we've done earlier. All right. Now we are looking at rotational kinetic energy. So same exact concept as linear kinetic energy. Same thing, just how much energy it takes, or how much energy is stored in something that rotates. In this case, we could say that rotational kinetic energy, I'm just going to say R, sub R for rotation, is equal to, it's like that's, imagine that disk I had earlier. It was made up of a lot of single individual points that are all pointed in specific directions. So let's first start with linear. Let's start with 1/2 mv squared. So that's linear kinetic energy. And let's convert that into angular velocity. So 1/2 m, it's v squared, so it's going to be r squared times omega squared. Okay. And then what do we have? We have, we could take the 1/2 out, 1/2 out, and we could take this mr squared. And what do we have? We have 1/2. The mr squared right there, that looks familiar. That looks like moment of inertia. I omega squared. So rotational kinetic energy, I'll put it at the bottom. Rotational kinetic energy is 1/2 I omega squared. This is really nice how everything kind of lines up with another form that we already know. So 1/2, some sort of mass, position, and a velocity squared. Okay. Let's see, I think I have 2 more things. Okay. Now we can talk about angular momentum. Some books have like a whole chapter on angular momentum. Our book has like 1 page. So I'm going to try to do as much as I can. We've talked about, in the linear sense, at the beginning of the semester we said, this is how things move, straight line. Okay, now here's kinematics for straight line. And then we went to forces, and then we went to momentum for things moving in a straight line. And that's with me crashing those cars together. Now that we're talking about rotation, we've talked about how things move, we've talked about forces. Now we can talk about angular momentum, the momentum of things that are spinning. So, let me put something right there. So, angular momentum is the symbol L. I don't know why. L. Actually, yeah, let me take that sign off. And that is R cross linear momentum. And that is a cross product. That is something we've seen in torque. I could say or. Maybe I don't like using that one. I'll say or. L is the moment of inertia of an object times the the angular velocity. So that's omega. So that's that fancy W. And so you might say, okay, this or that, why can I use both? I'll show on the next slide how I go from the one on the left to the one on the right. But for this bottom line, what it's saying is that if I don't add any more force to something that's spinning, I'm going to get these things spinning. So if I don't add any more force to that, then the angular momentum of the system is conserved. So pretty much says that if the sum of all the torques is 0, then angular momentum is constant. And that's a conservation of angular momentum. We've had a lab conservation of linear momentum. It's just looking at things before and after. Same thing here. I could say angular momentum before is equal to angular momentum after. That's what I mean by constant angular momentum. Okay. Now, how did I get that? I started with that cross product. R cross P. That's linear momentum. Was P, lowercase p. Well, I could say that's R cross mass times linear velocity, right? Okay. Same thing as I've done earlier. I don't want linear velocity, I want angular velocity. So let's change that regular V into omega. So how do we do that? We need to, let's go down here. Equals R cross M R omega. And technically, I need to include a sine of theta. Oh, that's the next step. Sorry. So now we have R. Maybe I didn't want the cross product anymore. Say R times R omega sine theta. And if this goes to 1, because I'm going to be having things spin perpendicular to their direction, then we have mr squared omega. That equals I times omega. Okay. All right. So that's how I just went from one form to the other. Let me do a little example of something with constant angular momentum. So I'm going to take these over here. Excuse me. Okay. Go like this. And this one. Okay. So I am going to be the rotating system. We have a chair here. And let me write up one thing also before I get going. I'm going to say, remember, if all of the torque is 0, then angular momentum is constant. Okay. So if we have this system and I start to spin and I don't apply any more torque, that means that the angular momentum of the system is constant, right? No one's pushing me more. No one's restricting me from turning. I just keep going. So the momentum is constant. Where's my axis of rotation? It's going like straight up through my body, right? So I'm spinning. The axis is straight up and down, straight through me like that. All right. Now, you look at these equations up here. The bottom line on the slide up here, that says that angular momentum is equal to the mass times radius squared times angular velocity, finally slowing down. Okay. So if we have L M squared, and if we have this value right here is constant, that means it can't change value. I can do this. So I can start out with a system where I have two masses and I hold them out from my body. And they are a certain radius away from the axis of rotation. Right? That one's down. They're hopefully the same radius. And I can start to spin. So we have mass, radius squared. What happens if I change the radius of these two masses out here? What else can change? So not my mass. I'm not magically going to get lighter or heavier. The only other thing that can change is omega, right there in that equation. So to bring them in, I speed up a little bit. Let me get something more significant so you guys can see it a little better. So the mass can't change, and I'm reducing the radius. Let me start out real slow with this one. So if I bring these in and get a smaller moment of inertia, that means that the okay. So if I have a reduction in radius, that means that the rotational or angular velocity has to increase. Yeah.
Isn't that so much like how ice skaters like pull their arms?
That's exactly why they do that. So it started out like this. And this is an ice skater, this is a gymnast, this is anybody who wants to speed up. And then slow down. And then speed up again. And then slow down. If I already start with its inward, go the other way. So it has a very small radius, then it's going to get a very large radius, it's going to slow down a lot. But the total amount of angular momentum is the same. I'm only changing where the mass is located. Okay. Try not to fall over. All right. So that is,
Is momentum still being conserved in the system?
yeah. Yeah, exactly.
Where is it going when you're increasing or decreasing the radius?
So let's go like this. So this I fixed to a certain number. And if this gets smaller, well, my mass isn't going to get bigger. So that means that the rotational angular velocity has to get bigger in order to keep this value the same. Right, so it's mass times this squared times velocity. If I extend my arms outward and I increase the radius, this value over here has to stay the same. Nothing else is forcing it anymore. So that means I can't magically lose mass. So that means the angular velocity decreases as I increase the radius. Good? Yeah.
Also, at some point, will you decrease in speed and eventually come to a stop?
Like due to friction and stuff like that, sure.
Okay.
But if I was in frictionless open space anywhere, then no. I would keep spinning forever. All right. Any questions on this angular momentum? That's okay. I think that's all I have for you guys today. So next time we will finish. We're pretty much done with the chapter, but we'll finish next time. And remember that homework is due on Tuesday before midnight. And you guys have a good weekend.